Okay. Welcome. Today, this is day 10, I believe, of class, of calculus class. Day 10 for you guys. So welcome. We've made it to double digits. So today we're going to pick up where we left off talking about the derivative. Specifically, we're going to finish up talking about the limit definition of a derivative. And then we're going to talk about some rules to help take derivatives that simplify that calculation that we've been doing over and over that nobody ever likes to do. Okay? All right, so before we start, a few announcements. Everything for the rest of the week is going to be virtual. So office hours tomorrow. Office hours tomorrow and class Thursday and Friday. Everybody's gonna Zoom in. Okay, Zoom in virtual because I will be out of town. You got homework due Monday, so the stuff we're learning this week, and a little bit. I put a few infinite limits on that as well. If you have any questions, ask me about it. Or you could ask the MEC. Go to the MEC, either drop in or schedule an appointment through STAR. Yeah, she knows. So yeah, the MEC, they're always there to help as well, just like me. Okay. Any others? Okay, no. So do we have any questions about homework or anything before we get started today? Okay, so yesterday we talked a lot about the limit definition of a derivative, and I never really talked about when a function fails to be differentiable. Okay, so when you can't take a derivative, or in other words, when that limit that you're looking at defining the derivative doesn't exist. Okay, so let's see, does the function f of x equals the absolute value of x fail to be differentiable anywhere? And if you forget what the graph of f of x equals the absolute value of x looks like, there it is right there. So we want to know, does this function fail to be differentiable anywhere? Well, looking at that graph, I mean, if I just cover up everything to the left of the origin, it just looks like a straight line, right? And I showed you, or actually I'm going to show you today with the limit definition. I think I might have covered one yesterday. But straight lines, the derivative is just a slope of the slope of a curve, the generalized slope. So a straight line, the derivative should just give us the slope back, right? So, and that's going to be the case. And same if I zoom in on the left and I just cover up the origin, that also just looks like a straight line. So hopefully we would just get the slope back on that side too. Where's the only place it looks like we might run into trouble in defining a slope for this curve here? Yeah, the origin, right? At x equals 0, it looks like we might have some trouble defining a slope there. So let's look at the limit. If it exists, f prime, oops. If it exists, f prime of 0 is equal to the limit as h approaches 0 of what? F of, yeah, and x for us is 0, right? Yeah, exactly. So normally we would have f of x is, really you could do plus or minus h, it really doesn't matter, but we usually put plus h. But it actually doesn't really matter if you put minus h. So f of x plus h minus f of x over h. But again, remember, we're looking at x equals 0. So I'm going to put 0 in everywhere I see an x. All right, well, this is equal to the limit as h approaches 0 of absolute value of 0 plus h. Well, that's just the absolute value of h, right? Minus the absolute value of 0. What's the absolute value of 0? Everyone, with one voice. 0. That was way better than I thought you guys were going to do. Good job. Yeah, the absolute value of 0 is 0. So then I'm just looking at the limit as h approaches 0 of the absolute value of h over h. And I've actually done it. Yeah.
Where do you get the absolute value?
Oh, so that's the function we're looking at. F of x for us. Yeah, excellent question. F of x for us is the absolute value of x. Good question. And so I've actually done this limit before. You might not remember. But this limit, if we look at the function, the absolute value of h, now we're letting the horizontal axis be h. If h is a positive number, so if h is bigger than 0, then what is the absolute value of h? For instance, if h is 10, then what's the absolute value of 10? Yeah, it's just 10. It's just, so if h is positive, then the absolute value of h is just h. Okay? So at 0, we don't really know or care what's happening, right? This is a limit, so I don't care what actually happens at 0. But absolute value of h over h, if h is positive, that's just h divided by h is 1, right? Does that make sense to everybody? Okay, so again, I don't know or care what's happening at h equals 0, so I'm just going to put an open dot there and then define h to be, not define h to be, h is 1. There we go. All right, sorry, absolute value of h over h is 1 for h positive. What about for h negative? If h is negative, so h is negative 20. What's the absolute value of h? 20, right? Yeah, so if h is negative, then the absolute value of h is you just take the negative of that negative number, right? And so if h is negative, the absolute value of h divided by h, well, that's going to be negative h over h is negative 1. Okay? And so, I don't know what's happening at 0, but I really don't care. And we get something that looks like this for h negative. And so, looking at this graph, so this is absolute value of h divided by h. Looking at this graph, what can we say about the limit as h approaches 0? It doesn't exist, and why? Why does this limit not exist? D and E. Well, what was something that we learned before about one-sided limits and the limit overall? If I look at the limit as h approaches 0 from the right of absolute value of h over h, that limit does exist, right? Because that limit is just, I'm zooming in on the right half of this. Well, that looks like it's approaching 1, right? As I approach 0 from the right. So that limit is 1. If I look at the limit as h approaches 0 from the left of absolute value of h over h, that limit is negative 1, right? Exactly. In order for the limit as h approaches 0, just no left or right hand limit talking about, well, the left and right hand limits have to equal each other in order for the limit as h approaches 0 to exist. Okay. So that's why this limit does not exist. Yes, perfect. Thank you everybody online for answering. That's why this limit does not exist, because we're approaching two different things when we approach from the left and from the right. So all that was to show that f prime of 0 does not exist, okay? It's not defined because that limit defining the derivative fails to exist there. Is everybody okay with that? Cool. All right, checking the graph. All the following graphs have a point where their derivative fails to exist. What do they have in common? So we've got three graphs here. We've got on the left, I'll tell you that that's actually the absolute value of x minus 1. The plot in the middle, that's equal to the square root of the absolute value of x. And the one on the right was just me playing around. That one's a weird function. I know what it is, but I'm not going to tell you yet. I'll tell you later in the semester. So what do all these plots, what do all these graphs have in common? And where would you say the point is that the derivative fails to exist? Yeah.
They're all V-shaped?
Yeah, they all are V-shaped, right? And so what in particular causes that derivative to fail to exist then? In a V, we have what? A sharp point, exactly. On this graph here, we have a sharp point right there, and that's precisely where the derivative fails to exist. Okay, and this is, again, it goes back to the left and right hand limits. When you look at the limit defining the derivative, the left and right hand limits won't be equal to each other. Same way right here, we have a sharp, this one's actually called a cusp because it comes in at an angle there, it comes in curved, but it's still a sharp point, right? It's where the graph turns sharply. And there's no way to kind of define the slope there. Because again, if I try to define the slope from the right, oh, that's cool. You can make an arrow. If I try to define the slope from the right, well, I don't want an arrow, then it looks like the slopes are approaching positive infinity, actually. And if I try to define the slopes from the left, well, that looks like they're approaching negative infinity. There's no way to really define the slope there. And the last one, again, this one's a little less clear that there's a sharp point, but there's a sharp point in that graph there. And so again, this one, the derivative from the left, it looks like it could be approaching, I don't know, like -1, it looks like. But from the right, it looks like a positive slope. Okay, so definitely the left and right hand limits won't be equal to each other. Oops, what did I just do? Oh, I don't care. Okay. Definitely the left and right hand limits won't be equal to each other. Yes, the point is what is causing this to fail to exist as a derivative. So if I give you a graph, the only functions that have derivatives are the functions that you can draw smoothly. So it's an even stronger condition than continuity, because who remembers if I give you, or I ask you to draw a graph, what it meant for it to be continuous? Yeah, you can draw it without lifting up your pencil. So all of these functions you can draw without lifting up your pencil. You just have to come to a sharp point and keep going, but you don't have to lift your pencil for that. Now, for smooth, or for functions that are differentiable, not only do I have to be able to draw without lifting my pencil, but I can't come to a point I can't come to a point, a sharp point, and keep going. So this kind of hints at what I'm about to say, and maybe you already know. But this isn't differentiable. It has to be something smooth. Okay. All right, so that leads into differentiability and continuity and how they're related. Okay, so before I talk about how differentiability and continuity are related. I'm going to show you an alternative form of the definition of the derivative. It's exactly the same thing, really, but sometimes, especially when proving certain results, this is slightly easier to work with. So this is an alternate form of the definition of the derivative. If f is defined in an open interval around x equals c, then f prime of c is equal to the limit as x approaches c of f of x minus c over, sorry, f of x minus f of c divided by x minus c as long as the limit exists. Okay. And so this is just saying, instead of before when I looked at the graph of a function and I was trying to define the slope. Oh, let me draw this in a different color. I was trying to define the slope of this curve at any point. Well, if I wanted to find the slope at the point C, before I said, well, we'll go over a little bit of distance, and I'll call that little bit of distance h, right? So this, before, we would call c plus h, and I would calculate the slope of the secant line through there, right? Now, all I'm doing is I'm just calling, instead of calling that little bit of width on the x-axis h, I'm just saying this new point here is, this new point here that we're using to approximate, I'm just going to call that point x. That's all we're doing. And then the slope of the secant line is, well, the height there is f of x. The height here is f of c. So the change in height is f of x minus f of c. The change in, or the change in the x is just x minus c, right? And then to get the derivative, you take a limit as, now instead of h shrinks down, and instead of talking about that interval shrinking down to 0, we're just going to talk about x sliding closer and closer to c. Okay? So really all we've done in this alternate form of the derivative is we've just renamed a few things. That's all we've done. Okay? But it is, for proving stuff about continuity, it is easier to work with. And so are there any questions about why this limit gives you the same thing as we talked about before? The limit as h approaches 0 of f of x plus h minus f of x over h gives you the same thing as this limit. Okay, so using this alternate form of the derivative, we can prove the following. If f of x is differentiable at the point x equals c, or in other words, f prime of c exists, then f of x is also continuous at c. Or in other words, the limit as x approaches c of f of x is equal to f of c. That's what we took as the definition of continuity. Okay? So, how can we prove this? Well, I'm going to prove something a little different, but equivalent. If I can show that the limit as x approaches c of f of x minus f of c is equal to 0, I mean, that's going to be the same thing as proving this, right? Does everybody see that? If I can show that, then I can show the thing above simply by adding f of c, because f of c is a constant. It really doesn't depend on x at all, so I can move it in and out of the limit at will. Okay, so if I can show this. All right, well, how is this related to that alternate form of the derivative? Exactly, that's the top of it. I need to use the differentiability of f in this proof, right? So I have the top of the derivative. We're trying to show that this equals 0. Now I'm actually going to show it. So we're getting rid of the equals 0. I want to show that it equals 0. I have the top of the derivative. Well, if I just put in the denominator, if I multiply top and bottom by x minus c times x minus c, then I haven't changed anything, right? If I multiply top and bottom by x minus c, I'm just multiplying by 1. Everybody okay with that? Okay. Also, because you might say, well, what if x is equal to c? But why don't I care about that case? Why don't I care about when x is actually equal to c?
Because you can't have the limit when you shouldn't look at the.
Perfect. Yes. When we're looking at the limit, I don't care about, that's really the only case that I don't care about, is what's happening when x is equal to c. I only care about what happens when x is close to c. So I'm not dividing by 0 here. That would be the only thing that could make this go wrong. Okay, well, who remembers? So now I'm looking at the limit of this big thing. How can I break this up into two things that I can work with? Who remembers the rules for limits? What would we like to do here? Well, I mean, why did I do this? To make this come out, right? Because that's the definition, the alternate form of the definition of the derivative that we'd like to work with. So I'm taking the limit of a product. Who remembers that if I take the limit of something times something else, that's the same thing as multiplying the limits together? Everybody remember that? So this is the same thing as the limit as x approaches c of f of x minus f of c divided by x minus c times the limit as x approaches c of just x minus c. Wunderbar. All right, what is that? Yeah. Yes, perfect. That is the slope of f at c, or in other words, the derivative, right? That is the derivative f prime of c. And what is this? The limit as x approaches c of x minus c. As x approaches c, what happens to x minus c?
Just c or minus c.
Careful. Yeah, I think you're thinking the right thing, but it came out a little wrong. Because you're thinking x is approaching c, not 0, right? So what's the overall function approaching? As x approaches c, x minus c is approaching. Well, we can look at a graph really quick. Here's c. So x minus c, well, yeah, it has a slope of 1. And so if I go, that means if I go up c, I have to go over c, right? The slope is 1, so the amount that I go up, I have to go over to the right the same amount. So that means here is c. So I have these 2 points on the line. So that's actually minus c, sorry. So what is the limit as x approaches c here of x minus c? Well, I'm going to cover, oh, oops, I need a bigger, fatter line. I'm going to cover that up. What does it look like this black line is approaching as x approaches, as x approaches C.
1.
Careful, this is the x-axis, y, and so it looks like it's approaching, it looks like it's crossing the x-axis, right? Yeah, so that's defined by y equals 0. So graphically, this is also a x minus c, that's just a polynomial, so that's continuous, right? So we can say that, yes, yeah, we can say that as x approaches c, x minus c, well, you can just plug in there because that's just a polynomial. So when we plug in c, we're going to get, we're going to get 0 there. So I'm going to get f prime of c times 0. But what is f prime of c times 0? 0. Okay. And so we're done. Does everybody see that we're done? Because we started really with, what we started with, I multiplied by x minus c divided by x minus c. So what we really started with was the limit as x approaches c of f of x minus f of c. Okay, so we started with that limit. We ended with 0. So that means that the limit as x approaches c of f of x is f of c. And we showed that the function is continuous at c. Okay. Are there any questions on that? Oh, question online? Yeah, we don't need an f of x minus c because we were just looking at when I only introduced a multiplication by just the polynomial x minus c, not f of that. And so that x minus c is just continuous, and I can just plug in x equals c when I'm looking at this limit right here. All right. So some examples. We're going to look at 3 examples. Find the equation of the tangent line to the graph of the function f of x equals x squared minus 9 at the point 1, negative 8. We're going to find the derivative of the function f of x is equal to 1 over the square root of x. And then we're going to find the equation of the tangent line to the graph of the function f of x is equal to 4x minus 3. And let's actually do these backwards. Let's start with number 3. All right, so I want to find the equation of the tangent line to the graph of the function f of x equals 4x minus 3. Oh, I forgot to give you a point. At the point 1, comma 1. Okay, well, in order to get the equation of a line, what 2 things do I need?
Slope and point on the line.
Yes, I need the slope and I need a point on the line. So what is slope? Or what is slope here?
4x.
Yeah, exactly. I didn't trick anybody. Yeah, this is a straight line. Normally, when I say the word slope, that should set off alarm bells in your head that you need to take a derivative, okay? When I say the word slope, you should instantly associate that with taking a derivative. But here, I was trying to trick you and I didn't get anybody. With a straight line, well, finding the tangent line to a straight line is just the line, okay? So really, number 3 is y equals, well, you know the slope is 4. If you want, you can do this in point slope form, but you're going to get the line back, okay? So if you want, you could do this as y minus 1 is equal to, you know the slope is 4, and then times x minus 1. But then when you simplify that, you get y is equal to 4x. So distribute there, minus 4. And then I add the 1 over to here, plus 1, which is 4x minus 3. Okay? So I didn't trick anybody. You guys are too smart for me. Yes, perfect. Thank you, Saba. Yeah, if you're trying to get a tangent line to something that's already a straight line, the answer is the line that you started with. Okay? All right, so let's do number 2. Find the derivative of the function, f of x is equal to 1 over the square root of x. All right, so this one, there is no trick here. So let's actually look at the limit definition of the derivative. I'm actually going to go back here, give myself some space. So I want to find f prime of x. And what is that defined as? Yep, f of x plus h. What else? Minus f of x, perfect. What else? Over h, perfect. And what's the last thing we need here? Careful. So this is good. This gives us a slope of a secant line. And what do I need to do to it to actually give me the derivative? Yeah, I need a limit. Yeah, don't forget that limit. It's very important. Very good. All right, well, this is just equal to the limit as h approaches 0 of 1 over the square root of x plus h. There's f of x plus h. Minus 1 over the square root of x. All divided by h, right? So that's just me plugging in what is f of x plus h, what is f of x, take a difference, and then divide. Zoom in. All right, so then we're looking at the limit as h approaches 0 then. What should I do here? Yeah, you can actually just jump straight to, I was trying to trick you guys again, but you didn't fall for it. You can jump straight to multiplying by the conjugate here, because this still looks like a minus b. So I can multiply by a plus b, and that'll get rid of the square roots, and that'll make it easier to work with, right? So I need to multiply top and bottom by a plus b. So I get 1 over the square root of x plus h minus 1 over the square root of x all over h. So I'm going to multiply this top and bottom by 1 over the square root of x plus h plus 1 over the square root of x divided by 1 over the square root of x plus h plus 1 over the square root of x. So when we do that, we get this is the limit as h approaches 0. Well, we're just going to get, this is a minus b times a plus b. So I'm going to be left with 1 over the square root of x plus h squared. It's just going to give me 1 over x plus h minus 1 over square root of x squared. It's just going to give me 1 over x. And then this is all divided by h times 1 over square root of x plus h plus 1 over square root of x. Okay, now what do we want to do? See if anyone online says it. Yes, perfect. We want to get a common denominator, right? it's specifically in the top. So the common denominator, again, doesn't need to be the least common denominator, because what even is that if you have an x? You just multiply the denominators together, okay? So this is x, I'll multiply top and bottom here by x. I multiply top and bottom here by x plus h. Okay, so when I do that, ooh, Chase is running out of room. This is the limit as h approaches 0. Well, in the top, I'm going to get, now the denominators are the same, so I can just add straight across the top. So I'm going to get x minus x is going to give me 0, right? And then I'll get another minus h. So I'm going to get negative h over x times x plus h. And then all of that is over h times 1 over square root of x plus h plus 1 over the square root of x. And then what happens with that h and that h? Yeah, those h's cancel. Okay. And now, so let me just erase that because I'm out of the room. So this is negative 1 over that. And now, what can I do? Yeah, now I can just plug in 0, right? I can, if I plug in 0, these are all algebraic functions that I'm messing around with. I'm multiplying, I'm adding, I'm dividing, but they're still all algebraic. So if I can plug in 0 and I get something that makes sense, then that's my answer. Okay, and so when you plug in 0, you get this, the h's go away. I'm left with equals. In the top, I have negative 1 over x squared divided by, in the bottom, I have this h will go away. I'll just have 1 over square root of x plus 1 over square root of x. So that's going to be the bottom 1 divided by 2 square root of x. And if you want to simplify that, well, I have a fraction divided by a fraction. So I can flip the bottom and turn it into multiplication, right? So this becomes negative 1 over x squared times 2 square root of x over 1. And for now, that's where I'm going to leave it. You can simplify this, and we actually are going to simplify this in a minute when we're looking at the power rule. But in order to get to other things, I want to move on. Specifically, I want to look at problem 1 because that's something you're going to be doing a lot. Okay. All right, so let's look at problem 1. Find the equation of the tangent line to the graph of the function f of x is equal to x squared minus 9 at the point 1, negative 8. All right, so now I'm finding a tangent line. I'm not trying to trick you. This actually is, you actually do need calculus for this problem. So in order to get the equation of any line, again, what 2 things do I need? Slope and a point. I gave you the point, right? 1, negative 8. You need to find the slope. And so what should be ringing in your head? The derivative. You should be shouting in your mind, I need to take a derivative, okay? And so I need to find f prime specifically of what point? I need f prime of 1. Perfect. F prime of 1 gives me the slope of this function at the point 1, negative 8. Okay? So f prime of 1, I'm going to go through this calculation at light speed, not light speed, but this is the limit as h approaches 0 of, well, f of 1, it was f of x plus h, but I'm plugging in x equals 1. So f of 1 plus h minus f of 1 over h, right? Well, f of 1 plus h is 1 plus h squared minus 9. Again, to do this, you have to FOIL it. On homework 1, I saw some troubles with this. So you need to FOIL this or memorize what it looks like. But this is 1, really 1 squared, plus 2h plus h squared, and then minus 9. Right? Any questions how I got that for f of 1 plus h? Okay, so this is then the limit as h approaches 0 of, well, 1 minus 9, that's negative 8. So I'm going to get negative 8 plus 2h plus h squared minus f of 1. Well, I already know that that's negative 8. So minus another negative 8, all divided by h. And so this negative 8 cancels with this negative 8. Okay, and so I'm left with the limit as h approaches 0 of 2h plus h squared divided by h. And what can I do now? Because every term in the top has an h in it, right? So I can cancel this 1h with 1h from every term in the top. And so I get f prime of 1 is the limit as h goes to 0 of 2 plus h, which is, yes, just 2. All right, so I have my slope. That's the derivative at 1. And I have my point, 1, negative 8. So I can write down in point slope form, and this is all you ever need. I don't, unless I specifically ask you to, don't go any further than what I'm about to write. Just write down from point slope form, y minus negative 8 equals slope 2 times x minus 1. I guess if you should probably change y minus negative 8 to y plus 8. That's the only simplification I want you to do. Okay? But that is a perfectly acceptable equation to tell me the line. Okay? Are there any questions about this? All right, you guys just, I think that was your first actual tangent line that you helped me find. You guys did it. You did all the work. Okay, amazing. And if you want, you can go into Desmos and plot x squared minus 9 and plot this line, and you'll see that it does line up. It's the line that just kisses the curve and then runs away forever. It's like my first girlfriend. That joke always kills. All right. Okay, so I don't think we're going to get into anything too deep here other than a constant, the rule for the derivative of a constant. So let's look here. So we're looking at basic rules for differentiation because using that definition of the derivative takes a lot of time, right? So we want in our toolbox a bunch of derivatives that we know how to take so that when we see them in the wild, we can just, instead of doing that limit definition, I can just say, I know that function, I know its derivative. Okay, so that's all we're going to be doing for the next couple of days, is figuring out just what the derivative of a general polynomial looks like, and then being able to write down the derivative without going through the limit definition. Okay, so today we're going to learn, actually probably Thursday, we're going to learn the power rule. If you've taken calculus, you definitely know it. If you haven't taken calculus, then great. Then I get to help you not form any bad habits. But if you have taken calculus, then that's okay. Okay, so first we need to figure out the derivatives of some simple functions. So the simplest function of all, just f of x is equal to a constant, right? What is the slope or the derivative of the equation of the function f of x is equal to 10? Let's find that from the limit definition of the derivative. What does it look like it should be? If I take any point, I come up here, what's the slope of this curve? Oh, careful, I gotcha.
0.
It's 0, right? It's a horizontal line. Yeah, careful. So it should be 0. If calculus makes sense at all, then we should get 0 here. So let's make sure we should be holding our breath right now. The limit as h approaches 0 of f of x plus h minus f of x divided by h. This is the derivative f prime of x, right? All right, what is f of x plus h? If I plug in x plus h into here, what comes out over here? Seems like a trick question, but I promise it's not. Yeah. Oh, careful. If I plug in whatever I plug in here, I always get out not 10 plus h. 10 plus 0. Yeah, just 10, right? This notation here says f of x equals 10 means whatever you plug in to f, you're getting 10. Whatever you plug in. If you plug in 10 trillion, you get 10. You plug in h, you get 10. So this is the limit as h approaches 0 of this is just 10. 10 minus this is just 10.
Isn't that whole thing just 0?
Perfect. Exactly. That's exactly the point of this. And this is equal to the limit as h approaches 0 of 0, really over h, but 0 divided by h is still 0. And that's just 0, right? Yes, excellent observation. So it checks out. We just decided that the slope of a horizontal line is 0. Nothing groundbreaking, but calculus checks out with our intuition here, right? So you can see that 10 didn't really play a special role here. I could have plugged in any constant number there, and this process would have shaken out the exact same way. I would have taken whatever constant minus that same constant, I still would get 0 in the top every time. Okay, so with a minor change, with a very minor change to f of x equals 10 to f of x equals a constant, you can show that the derivative of any constant function, if f of x equals c, where c is a constant, then f prime of x, the derivative, the slope, at any point is 0. Is that too controversial? All right. What is the derivative of the function f of x is equal to negative 3x minus 5 over 2? All right, let's find it. When I say derivative, again, what word should be screaming in your mind? Slope, right? So what do we think the answer should be? Right, yeah. If I was finding the tangent line, I would just get that tangent line back, right? And so what, specifically though, what slope should I get? Negative 3. I should get negative 3 here. Let's see if that's true, and then we'll head out. The limit as h approaches 0. Again, I'm trying to find f prime of x. So this is the limit as h approaches 0 of f of x plus h minus f of x divided by h. This is equal to the limit as h approaches 0 of negative 3 times, in parentheses, be careful here, x plus h minus 5/2. Need to zoom in a little. Minus 3x minus 3x minus 5 halves, all divided by h. This is equal to the limit as h approaches 0 of, well, I distribute this here and here, negative 3x minus 3h minus 5 halves plus 3x plus 5 halves all over h. And so as you can see, by magic, that cancels with that cancels with that, and I'm left with a beautiful 3, negative 3. I can write. There we go. Does that make sense to everybody? All right, and I'll just mention right before you leave, there's really nothing special about negative 3 and negative 5 halves in this. If I did any straight line with a slope m and a y-intercept b, this calculation again would have shaken out exactly the same way. And so you can prove that if f of x is a linear function, f of x is equal to mx plus b, then f prime of x is just equal to m. Okay, all right. Feel free to head out. Thursday, we're going to talk about the power rule, so be ready. It's a great rule. Please wipe down your desks as you go. Anybody online? And Saba, yes, thank you. You're right about factoring out the square root. It's actually 2 over x to the 3 halves. Thanks, guys. More.